Good day to you. This is Anagalactic bringing you another science presentation in astronomy. We've gone from astronomy to the edge of the universe where we encountered infinity, and that caused us to switch tacks to cosmology to see what science has to say about the edge of the universe. And from there we discovered the redshift is critical to the current cosmology, and in order to understand redshift, we need to understand the geometry of light. And so that turns us to quantum mechanics. There are two sides to quantum mechanics, as there are two sides to virtually anything in the human equation. Quantum mechanics is baffling. It baffled Einstein, so we can expect that it's going to baffle pretty much anyone else. But there's another side to quantum mechanics that's remarkably simple. It's curious because there is a paradox involved. What we're going to look at right now is a brief clip from a Lex Fridman podcast. This was a while back, a few years, but not too long ago, where Lex had on Sir Roger Penrose, and they had well over an hour of conversation, well watched, well appreciated. It was called a classic by some of the commentators, and I believe it is a classic because Lex Fridman is an extraordinary interviewer. He does an amazing amount of background research for each one of his hundreds of interviews with top-notch physicists. And it's fairly safe to say that the top of the list of any of his guests has been Sir Roger Penrose, who is still around and going. He's 92 years old. One of my heroes. I've read his book called The Road to Reality. I call it The Laws of the Universe. And I wore out the spine of that book, taking notes backwards and forwards on Sir Roger Penrose's book. He has a unique insight into the three cutting edges of physics right now. One of them being cosmology, where he has introduced an alternative to the Big Bang, which he claims has been disproved. He is correct, of course, but then that leaves open the question, what is the correct, or at least what is the better cosmology? Dealing with either the origin of the universe, if that can be discovered, or at least some idea of the structure of the universe. Science does have this task, which is now immense, of somehow explaining the macro structure of everything. Well, that is quite a daunting task, and that is the province of cosmology. The most, I would say, strange aspect of physics is attempting to get a grip on the entire universe, but it is something that science will definitely attempt and has been doing so for about 100 years. So that's one cutting edge. The other cutting edge is at the opposite end of the spheric spectrum, the infinitesimal at the center of all things. We call that the proton, and there is now a mathematic structure for the proton, but no further particles can be derived. None of the cyclotrons, which are now called hadron colliders, have been able to isolate a quark. And a quark is a pure mathematical concept. You will see it listed in the standard model of particle physics as a particle for reasons I've discussed. There's no other word. You could say it's a wave, but then that's not really a thing. And that's the quantum paradox, is that a wave is not really localizable. And that is the quantum paradox. Sir Roger will be talking about that today in our very brief clip from Lex Fridman's classic interview with Sir Roger Penrose. The first half, approximately, of this lecture deals with Lex's preferred topic. Excuse me, let me take off my reading glasses. Which, of course, is artificial intelligence. And one of the hallmarks of this lecture, since it is Sir Roger Penrose, it's not some wacko like Yudkowsky or any one of these other basically psychotically oriented speculators who are simply trying to make money and make a living, so don't put them down. Let me put them down, because they can take it from me since I'm nobody. But Sir Roger is not a wacko in any way, shape, or form. And the hot topic, the maniacal topic, which is promoted by the government, indirectly you could say, or however you interpret those things, the other side of life that we scientists have to face when we come out of our laboratory, the cold, cruel world of governments. Oh, crap-a-looey. Well, can artificial intelligence machines achieve consciousness? The answer is, of course, no. But science is relentless. You have to be able to prove it one way or the other. Well, Sir Roger took up the cudgels. He accepted the challenge, and he spent quite a bit of time researching into neurophysiology to try to get at the root of consciousness in terms of this psychotic, schizophrenic, maniacal, crazy, anti-scientific notion that machines might become conscious. Now, my take on that, since I interpret things for the layman, you can get a firm grip on that subject using a strictly geometric approach. Can a machine ever become conscious? No. Why not? Because a machine cannot have a point consciousness. A machine is a distributed series of electronic connections, and that cannot form a consciousness because there's no center to the goddamned thing. And that's the end of the story. No, it's not, okay? I just say that so you'll have some kind of frame of reference to deal with this logically, because you know it's impossible. There is no such thing, and there never ever will be such a thing as machine consciousness. But everything short of that, that's what the government wants, because machines are extraordinarily efficient killers. And there are whole armies of robots all set in China. It's well known. The United States has the same thing. Drones are robots, and you can make them as intelligent as you want. But that intelligence is the evil intelligence of governments who are out to murder people. That's all governments do, is try to conquer each other. Well, we're not interested in that. We're into science. And we're not merely into science. In this classroom, we're into heavenly science. Nothing to do with the Earth, except as the Earth is an astronomical object in space. Just happens to be occupied with humans, and we just happen to be those humans. Lex Fridman, although he does have on 98% wackos, he's simply trying to make a living. There's no blame here. I like Lex a lot. I think he's extraordinary. But his it's not forte, it's fort. I'll say it for Americans, his forte is not really science, certainly not at the cutting edge of science. Lex is an entertainer, and I mean that in the highest respect. I admire Lex totally, but I'll tell you something else about Lex. That man is extraordinarily right on. He's intelligent, he does his homework, he cares, he's a real human, he's trying to deal with this stuff in science. And he's into artificial intelligence, so of course he's after the controversial side. Well, everyone knows what that is. Conscious sentient robots. Never will be such a thing. You can just write that off. Not in science, he can't. You have to prove everything. So Sir Roger has an excellent approach. I strongly recommend any interview with Sir Roger Penrose on artificial consciousness or cosmology, or today what we're going to look at, his take on quantum mechanics. And from there we're going to get into our current topic today. That's 10 minutes of bracketing information. Let's go. The name of this lecture is Lineospheric Imaginarity. Now there's a big mouthful for you. I do like big words. I confess, I'm a wordsmith. I was measured for, my relative intelligence in certain areas. Mathematics is just about, well, it's measured at 82% at Stanford, which is high, but it's not enough. You got to be in the 99th percentile to get into science on the mathematics side. You practically have to have been bred for it. You have to have been controlled in your birth sequence with some kind of pseudo-evolutionary selection to make a mathematician today. I don't even understand how these men can exist. I admire them totally, but I also can see through the bullshit. And they're stuck with their linear shit. And we're going to get through that. We're going to make sure that science can progress. It has been halted in all three of these areas. Quantum mechanics has been absolutely halted. You could say since John S. Bell, which is quite a while back. But I say it's been halted for 70 years. I say it's been halted for 100 years. I say nobody has ever understood quantum mechanics. And Sir Roger Penrose, you're going to hear him say the same thing. But with some value-added information. We have to understand quantum mechanics. There is no way this situation in science can continue with these maniacal guesswork systems. Science doesn't do that. It's been doing it for a century in quantum mechanics, and oh, the governments love it. The governments love this kind of situation. Okay, I've been through that before. No more ranting, that's 13 minutes. Let's hear what Lex Fridman pumps out of Sir Roger Penrose, one of the greatest scientists who's ever lived. Here we go.
But they're not all the same kind. You get different kinds of microtubules. They're very, very symmetrical structures. And I had reason to believe that these very symmetrical structures would be much better at preserving a quantum state. So you had to preserve these quantum states at a level which the state reduction process comes in, and that's where I think the non-computability comes in.
So something about the measurement process and what's going on, something about the structure of the microtubules.
Yes.
Your intuition says maybe there's something here. Maybe this kind of structure allows for the mystery of the.
There was a much better chance. Yes, it just struck me that partly it was the symmetry.
So we've got to take a step back just to say, in case people are not familiar. So that's counter to the notion that consciousness might arise from the computation performed by the synapses.
See, sometimes people say it's because it's quantum mechanical. It's not just that. See, it's more outrageous than that. You see, this is one reason I think we're so far off from it, because we don't even know the physics right. You see, it's not just quantum mechanics. People say, oh, quantum systems and biological structures, no, will use. But you have quantum effects, which are not just chemical, in photosynthesis. And this is one of the striking things in the last several years, that photosynthesis seems to be a basically quantum process, which is not simply chemical. It's using quantum mechanics in a very basic way. So you could start saying, oh, well, with photosynthesis is based on quantum mechanics, why not behavior of neurons and things like that? Maybe there's something which is a bit like photosynthesis in that respect. But what I'm saying is even more outrageous than that, because those things are talking about conventional quantum mechanics. Now, my argument says that conventional quantum mechanics, if you're just following the Schrödinger equation, that's still computable. So you've got to go beyond that. So you've got to go to where quantum mechanics goes wrong in a certain sense. You have to be a little bit careful about that, because the way people do quantum mechanics is a sort of mixture of two different processes. One of them is the Schrödinger equation. It tells you how the state of a system evolves, completely deterministic, but it evolves into ridiculous situations. And this was what Schrödinger was very much pointing out with his cat. He said, you follow my equation, that's Schrödinger's equation, and you could say that you have to a cat which is dead and alive at the same time. And he's more or less saying this is an absurdity. There's something missing. Reduction of the state or the collapse of the wave function or whatever it is something which has to be understood. It's not following the Schrödinger equation. There's something more than that. And it's easy to quote authority here. At least 3 of the greatest physicists of 20th century who were very fundamental in developing quantum mechanics. Einstein, one of them, Schrödinger, another, Dirac, another. You have to look carefully at Dirac's writing because he didn't tend to say this out loud very much because he was very cautious about what he said. You find the right place and you see he says quantum mechanics is a provisional theory. We need to go beyond the theory we have now. I happen to be one of the kinds of people, there's a whole group of people, they're all considered to be a bit mavericks, who believe that quantum mechanics needs to be modified. There's a small minority of those people, which are already a minority, who think that the way in which it's modified has to be with gravity. And there is an even smaller minority of those people who think it's a particular way that I think it is, you see. So
those are the quantum gravity folks. But what's...
You see, quantum gravity is already not this. Because when you say quantum gravity, what you really mean is quantum mechanics applied to gravitational theory. So you say, let's take this wonderful formalism of quantum mechanics and make gravity fit into it. So that is what quantum gravity is meant to be. Now I'm saying you've got to be more even-handed, that gravity affects the structure of quantum mechanics too. It's not just you quantize gravity. You've got to gravitize quantum mechanics. And it's a two-way thing.
But then when do you even get started? So that you're saying that we have to figure out a totally new ideas in there.
Exactly.
I hope you enjoyed that. So the summation of this, in my opinion, is you'll notice at the end that gravity was brought in. Of course, this is now referring to the unified field theory, which is the highest goal of science right now, is to unify the theory of gravity, which is Einstein's, with the theory of quantum mechanics. A couple of interesting points are brought out here. These are not new points, but they're points that need to be borne in mind. There is no theory of quantum mechanics. And Sir Roger brought that out quite carefully. The Schrödinger equation is a deterministic equation which does make accurate predictions about quantum mechanical phenomena. But there is the state, and the state is really what we're after in physics. It's fine to make predictions, but we are making predictions about state. And when he refers to Schrödinger's cat being dead and alive at the same time, he's referring to the fact that that's an absurdity. And it's just the way it is in this paradox that using the deterministic equations of Schrödinger, both the time-dependent and the time-independent versions of Schrödinger's famous equation, leads directly to the paradox in this particular context. The paradox has several contexts. We're getting to the one that we want, which is light propagation. But all of this fits together into the same paradox system. I call this the quantum mechanical paradox complex. The fact that it's a complex is significant because now we're talking about structure. And the common aspect of the structure of this complex is something imaginary. It's obvious that this imaginarity is brought forth in the dual state of the cat. Schrödinger was lampooning the theory because there is no theory. So essentially, he's pointing out that we still need a theory. And that is what Einstein said. And Sir Roger also carefully pointed out that this was also Paul Dirac's view, that this is a provisional theory. That is, the equation of Schrödinger is provisional because it produces a state where the cat is both alive and dead. This is called entanglement, and it's also called superposition. Actually, I should say that's really superposition. It's the superposition of the dead and alive state. And the reason Schrödinger chose to kill a cat, which I'll bet that he likes cats, he was trying to point out how serious this is. That his equation that he invented, he didn't even like it. That matches Max Planck's discovery of the quantum. He actually tried to deny his own discovery because he didn't like it. And it's worthwhile reading what Max Planck says about his discovery. He said it was an act of desperation. But it began the quantum revolution. Paul Dirac came along, and his place is immortal in the quantum scientific world because he introduced a relativistic solution, which is somewhat different from, or different than, I believe the British and American usages are different from and different than, but they're equivalent. I don't know which I prefer anymore. But the Dirac equation is different from the Schrödinger equation. What we're concentrating on here is the superpositional state, because the way Sir Roger brings this out, and Lex is in agreement, that's how we closed that little segment, we need to have an explanation for the split state. This is what Einstein called spukhafte Fernwirkungen, which is a term which has been around longer than Einstein, but not in German, and not in those exact words. Newton dealt with the same basic situation in his formulation of gravity, is spooky action at a distance, and he wasn't quite sure what that meant, but according to what Newton says in his famous book Principia, is how it's usually shortened, he says it's not his job to interpret. His job is to measure. Well, now in quantum mechanics we have something called the measurement problem, which introduces all kinds of spooky aspects to what are the experimenters doing when they force the collapse of the wave function. This has led to the extraordinarily famous and popular many-worlds theorem, which Bernardo Kastrup does not like. But unfortunately, Bernardo takes basically a mystical view, and he's not the only one who does this. The many-worlds theorem itself is a mystical view, because it says that reality splits. Basically, the universe splits. So that if the cat is alive at the end of the experiment, that means another universe split off with a dead cat. Well, of course, that is simply mysticizing what happened. What actually happened was, in the superpositional situation that is forced by Schrödinger's wave equation, in order for that equation to work, there has to be a split state, which it's some measure, well, immeasurable or measurable, no one's sure, but it's some interim between this first state and the second state. There's an interim state where the cat is both alive and dead. And it's just paradoxical, nobody can get around it, that for a while they're both true. Well, what does that mean? That's really the quantum paradox. Well, I have the solution. It had to be geometric. Of course it's geometric. You can approach this in several ways, and entanglement is closely related to superposition, that you have two particles in an entangled state. And when you measure one particle, it instantaneously changes the state of the other particle, which violates light speed. There's no actual transfer of information, so all of these Alice and Bob experiments, you can forget them. And the whole crypto, the whole idea behind quantum computing is to get a one world government stranglehold on the monetary system of Earth. That's why the governments are supporting quantum computing. Now, none of the men, such as Scott Aronson, whom I studied under, these men are not trying to support the government. They couldn't care less what the government does with quantum computing. But that is why it's being funded. But it's fascinating in its own right, for the same reason that nuclear fusion is of incredible importance to scientists who are not trying to destroy humanity, but the governments are. And we don't deal with that. We simply don't care what the governments do with this knowledge. Evil is going to get hold of anything we discover and use it for governmental purposes. Just pure evil. Well, that's part of the human equation that we have to deal with on our own time. Science doesn't deal with it. We simply deal with the facts, ma'am. Get the knowledge, get the understanding, and try to answer our own human questions on an individual basis. But it is collaborative and it is consensual. We're all in this together somehow. My goal is to get the answer to the quantum paradox so that we know what reality is. We need that. Because we need to know about the flight of the photon, we need to know about how light propagates through space. And the reason we need to know that is so we can reinterpret the redshift of cosmic light. Because the universe, children, is not expanding. But you might think so if you interpret redshift as Doppler shift. It's not Doppler shift because it's not sound. Doppler shift only applies in a medium such as an atmosphere. Light does not do that, but it does have a redshift and a blue shift. Just as sound waves have a compression which raises the frequency, and then when the train passes, it decreases in frequency. That is the sound equivalent of blue shift and red shift. But light does not do that. It does something much spookier. And here's another point I wanted to bring out, which Sir Roger comes through. I'm totally with Roger on his point of view, that quantum mechanics is not spooky enough. He's trying to address the question of consciousness on behalf of Lex Fridman's interest in AI, which Lex Fridman is an AI presenter. So he wants Roger to comment on artificial consciousness, which is absolutely insane. There can never be such a thing, and don't even give that a moment's thought. However, what happens in this confrontation, really it's a confrontation at 2 points of view. The government really wants this to be exciting to the public. Well, artificial consciousness has been popular for centuries. There have been stories that have been bandied about forever about a machine that comes to life. And Mary Shelley with her Frankenstein is just one more variation of a much older story. There's a story of Picodiri Bibi. I know, but it's a funny name. And Henry Miller taught me this, but I looked it up and there really is a Picodiri Bibi, which is a machine that came to life. It was a story that was invented centuries ago. So there's no such thing. But why is it so attractive to the science fiction mind? Oh, it's because of consciousness, the mystery of consciousness. We're going to get into that, but that's 33 minutes. And I hope you're ready for some really deep stuff. And I'm just going to broach the topic here that's going to be in the next lecture, obviously. Lineospheric Imaginarity. And here's the kicker, so you'll tune in. the nature of entanglement is two separated particles, where when you change the state of one by measuring it, it instantaneously changes the other. That is an exact equivalent of the collapse of the wave function, because as we discovered from Christian Huygens, whose discoveries are well accepted in optics, all of science accepts the fact that the propagation of a photon, that is light, is photon, right? Well, the propagation of light as a photon is as a spherical wavefront. Well, that means it has a radius as it expands, and that sphere expands. And when it gets to your photographic plate or your eye, the whole sphere collapses at once, in no time at all. And Einstein just lost his shit over this. He couldn't stand it. And so what he said is your quantum theory, and it was partially his theory, let's not forget that, it's Einstein who proved the particle nature of light. He got the Nobel Prize for it, and we all accept photon. You learn of it in Star Trek. The photon is a particle. But is it? Well, one thing we can definitely say about it, it's a geometric object, because a sphere is a geometric object. That is the secret. We're not measuring the spherical component of light on its own terms. We're always using linear numbers. We use linear algebra. Space-time is a linear system of 3 orthogonal lines, which makes cubic space, plus a fourth imaginary axis, which is orthogonal to the other 3, which really is hard to visualize. Well, it adds a spheric function. For the same reason that complex numbers, a 2D system with one imaginary axis, you see the relationship. Space-time is a 3 linear axis spatial system with a fourth imaginary axis. The only problem with that is the 3-1 split. It's obvious that Einstein got it. Space-time works, but the way it works is with 4-tensor calculus with a gamma term in pseudo-hyperbolic space with a light cone. That simply is incorrect. The light does not travel as a cone no matter how you look at it. It travels as a sphere. Now, that's not quite fair to Einstein because he wasn't specifically addressing light propagation. He was addressing the opposite. Light propagation can be conceived as a centrifugal force, as I've proved, and you can check the previous 3 or 4 lectures for that, or the previous 350. But gravity is a centripetal force. It's the integral protonic force, of course. It's bending space. But as space bends, something has to be said about time. Now, what Einstein said is that space is 3 and time is 1. What I've discovered is that space-time is 2, which is obviously correct. But we don't have a mathematics for it. That is, we don't have an algebra for space-time. The space-time algebra that's being used is 3-1. It's an extension of complex imaginarity. The imaginarity comes from the square root of -1. You really have to see that to appreciate why it creates a circular function in the plane. Think of the square of 1. The square of 1 squared is 1. That's magical. Because it's the same 1 in square space. It's a different metric, so that you have a square that's 1, but it's made from 2 sides that are 1. So the 1 times the 1 equals 1 in another form. That's magic. That leads to the Pythagorean theorem, which is why we're able to get at circular and spheric space with the Pythagorean theorem. It's because of the peculiar nature of the number 1. Well, then there are the negative numbers, which are not used in distance measurement. Everything in the universe is positive. There are no negative distances. And I've already taught you that the line is only useful for linear spatial separation. Now, you can use the other direction. And you do need both directions because that line has two directions, right? And one of them is negative. If you're using linear spatial separation, then the index goes forward 1, 2, 3. But as it does so, there's a negative effect of -1, -2, -3, which is balanced on 0. It's balanced on linear 0. That's the definition of add on the line. And that's been proved, so you can accept that. That's so simple that it may sound mysterious, but it's so simple that it leads to an extraordinary insight. Because what is multiply? That's a 2D operator. Because 2 times 3 makes a rectangle. But 3 times 2 makes a different rectangle. They both make 6, but they're oriented at a 90-degree angle. We're taught that multiplication is commutative. No, it's not. It's not commutative. And so here's the point. Pardon the pun. If you go negative and use -1, if you take its square root, that's the inverse of the square. Well, what happens since it's negative and you're taking the inverse of the square, it does something else magical, but it's not linear. It is linear until you learn about the magic number e, which is its own derivative. It's a very magical number. I believe it's 2.71828. It's a magic number because it's its own derivative. And if you use e with the square root of -1, it makes a perfect circle on the plane. And that's why e to the I pi power equals -1. Because when you start at +1, you do this right, +1, and you multiply, you're actually taking a power of e, which is its own derivative. If you take e to the pi power, that produces a real number. But if you take e to the imaginary pi power, that's pi times the square root of 1, and that's the exponent. E to the I pi power goes to -1 on a circle. And that has been proved. You can accept that, but that's extraordinary property of -1. What I've discovered is you can do that without using negative numbers. You need proportional numbers which produce spheric space. So I hope you stay tuned. That's 42 minutes. That's the max for an American audience whose attention span is that of about a mayfly. So without meaning to insult you, except to improve you, I hope you tune in for the next lecture. This is Anagalactic bringing you the secret of the universe so we can understand entanglement and superposition, so we can crack the quantum mechanical paradox for the first time in human history. I have done so. In order that we can understand redshift of cosmic light, so we can break the bounds of cosmological expansion, which is insane. It makes no sense whatsoever, and get rid of the Big Bang, which makes no sense at all. And from that we can get back to the origins that we need. You also need to know your human origins, and you're being lied to about that, and all the top scientists are lying. If they were put under a lie detector test, I would bet money that they'd all, or most of them, would pass it when they say that natural selection is a scientific principle. But they all say it because they have to. But it's not true. It's been disproved. And so your origin as a human, the human race, the ecology of Earth, is a total and complete mystery. we have no idea where the ecology came from. And I think you know where that leads. You're going to have to believe somebody about that. You don't have to believe anybody if you're a scientist. You're allowed to say that you don't know. But if you say that you're descended from amoebas and monkeys, you're a goddamned liar. That's been disproved. This is a much higher calling than any religious calling. Science is religion because it's logical. It connects humans with the universe, our only source of reality. And if you believe schizophrenic liars about how we're descended from monkeys, then you're a sucker. So we're going to get both answers. Stay tuned to Anagalactic for the secret of the universe, the solution to the quantum mechanical paradox, only from Anagalactic. We'll be right back. Keep looking up.